Thanks so much for having me, even though I have to be remote today. I'm excited to talk about soft wearable haptics enabled by distributed stiffness, and it's so perfect for me to go after Joshua and Irene because so many of the things that they said, I agree with 100%, and they provide a great foundation and context for some of the things that I would like to discuss. So let me actually start by acknowledging the students and postdocs who are primarily responsible for this research. A lot of this is led by my postdoc, Cosima Dupesque, who finished her PhD at ETH Zurich a couple of years ago and is now a postdoc in my lab. My PhD students, Sehi Jiang and Jasmine Palmer and Crystal Winston, and then a former postdoc, Zenishbek Zakipov, who is now at Apple. And these are the hardworking folks that whose work I get to present today. So in the context of this workshop, what's already been mentioned actually by Irene, some of the prior work that my lab had done with multiple degree of freedom of skin deformation feedback on the fingertips. And I wanted to start by just talking about a little bit about our journey from hard to soft. So when we originally started working on this, inspired by work from Domenico Praticizzo's group, we wanted to provide multiple degrees of freedom on the fingertip such that you would just get cutaneous feedback rather than cutaneous plus kinesthetic when you picked up virtual objects. And we use these very traditional sort of electromagnetic actuators and design techniques from robotics that basically made a little Delta robot that sat on your fingertip. It was very effective, but as mentioned by both Irina and Joshua, we're trying to figure out how do you make these devices lighter weight, less expensive, et cetera. So then in recent years, from this first design, we've worked on origami versions on the upper right view now, which actually is bulkier and maybe not as pretty as the original electromagnetic version, but because it uses lightweight folded materials using origami approaches, it's actually quite a bit lighter. And it actually has 4 degrees of freedom beyond the 3 degrees of freedom of our original device on the left. And then in collaboration with Jihuan Ryu's lab, we also started trying to develop, basically use 3D printing in order to make soft components within a rigid device. And so there's another example here in the middle of a work in preparation where we have a fingertip haptic device, in this case, 3 degrees of freedom, where we avoid the traditional joints and such using soft materials. And then on the lower right, the one that I'm probably most excited about in terms of our fingertip devices is a version that we first presented at RoboSoft in 2022 that we're still working on a final version for journal publication, where the idea is now we monolithically 3D print a soft wearable fingertip device. In this case, it has 4 degrees of freedom, and it actually operates by vacuum. I won't get into too many of the details of this particular device because I mostly want to focus on our knitted wearable haptic devices. But the idea behind this device is one that we've really been trying to push in our newer devices, which is that you really distribute the stiffness by modulating material properties or sort of thicknesses and geometries in different parts of the device. But you try to produce these devices sort of monolithically so that you don't have in soft robotics, one of the main challenges is like delamination and attaching hard things to soft things. So this example here with this 3D printed device is it's monolithically 3D printed out of one material where we just make it thick and thin in different locations in order to get the properties that we want. And we're also doing this in the new work that I'll talk about in a little bit. So we are also moving off the fingertips towards other parts of the body. So we want to free the hands for virtual interactions via devices, because we want to also add on real interactions with real objects. So actually, I thought it was really interesting that Irina discussed that with her pneumatic unit cells, that you could still do hand tracking. And that has been a challenge for us in the past, although we haven't done this completely with silicone. So it's great to hear that with silicone only, you might still be able to do hand tracking. But nonetheless, even if you can do hand tracking, if you want to have augmented reality, you want to be able to touch a real object and then touch a virtual object having the hands occluded is a challenge. And bigger picture, I'm very interested in like, what does it mean to have a haptic augmented reality? It's kind of clear in vision that you can overlay things visually. But in haptics, you get this kind of physical obstruction from the haptic device if you want to overlay real and virtual objects. So one of our approaches has been to take devices off from the fingertip and move them into other parts of the body, like the wrist and the arm. But there's a lot of challenges in doing so. One is a sparser distribution of mechanoreceptors on the hairy skin of the arm and other locations compared to that of the fingertips, where it's very dense. And another is sort of the challenge of active versus passive touch. When we explore objects like this, right, we actively will move fingers around in order to learn about mechanical properties of the world. However, if we provide feedback in other locations of the body, like the arm, we're used to receiving passive touch there. Like we're not used to actively exploring the world with feedback in those locations. So there's some funny perceptual questions that I think our community still has to really answer. For example, if you go and you touch a virtual object with your fingertips, but you get the feedback somewhere else in the body, how much worse is that? How do we interpret that information? Because we're used to using certain parts of the body for active touch and other parts for passive. So in terms of the design of these devices now that are going to go on the forearm instead of on the fingertips, I'm going to talk about a bunch of things that we've tried over the years, which in the end, I don't really think are the way to go. So one of the first things we tried is using a classic soft robotic structure, as shown here on the left, which are fiber reinforced elastomeric enclosures. And the idea is there was that could we provide these same shear directions? I know there's a question in Irina's talk about, oh, what about shear? For starters, it turns out that shear is much more difficult for people to detect on the arm, but also in general, it's like, how do you create a structure where you provide the necessary reaction forces so that you can generate the shear? And you can see in this video on the left how awkward that is. We wound up having to create a kind of rigid structure within which to house the soft robot haptic device. And that just made for a really bulky, unattractive, uncomfortable device. And so the advantages of softness that we wanted in terms of wearability were not really realized in this device because you needed to have this rigid structure around for reaction forces. So on the right, we have a totally different type of concept where we were inspired by other work in my lab on these soft growing vine robots, where we had to try to have them grow on the arm. And this was sort of fun as a concept, but practically not super compelling. The main thing I want you to get away from comparing these two types of devices on this page was that the one on the left is that we had a single point of contact where force feedback was happening in two directions of shear, whereas on the right, it was more like a squeezing effect. And then we also had little pouches on the inside. So these are multiple points of contact, but the information is single direction, not providing shear. So some other devices on the left, this is another attempt to make elastomeric, fiber reinforced elastomeric enclosures that provide multiple degrees of freedom. But once again, you have this really rigid structure that we needed to put into place in order to have the necessary reaction forces. So you can see not, again, super compelling for wearability. And then we took the fingertip 3D printed device and also tried to make another version of that was larger and would create what we called hoxels or haptic voxels that would provide multiple points of contact on the skin. And this one on the right does work pretty well, and we're continuing to study it, but it is still relatively bulky, and it's probably trying to do more degrees of freedom than what people can actually interpret on the forearm. So moving forward, we have this interest in social touch, and Irene mentioned she shares a lab with Femke van Beek, and Femke was actually at Facebook Reality Labs at the time that we were collaborating with her group on the potential to provide distributed feedback for social touch. And Irene's comment about not providing multiple degrees of freedom, but instead giving a parent illusory motion feedback is exactly what we tried to do here. So if we wanted to simulate the idea that you're sliding a finger across the skin, for example, to say, calm down or something like that, we had these series of actuators that if you put them in the right order with the right speed and the right spacing, you could give the illusion of a continuous and pleasant touch. And we did this in this first case, not with soft robotic techniques, but rather with traditional voice coil motors, which were not great. Overall, each one is heavy. They actually heat up over time. We weren't just using them for vibration, but also for static pushing forces. And that really means overdriving them and they heat up. And so it actually results in a pretty bulky device. And we did manage to fit it into a sleeve, but it wasn't great. So we're trying to figure out how do we take these ideas from soft robotics and soft haptics and things like social touch, where we create this illusory motion, and how do we put this into a smaller, more compact, lightweight, comfortable device. A few other things before I go there on the continuous stroke illusion. I did want to talk a little bit more about this question of degrees of freedom. So we can give this illusion of a continuous stroke just by having a series of normal forces on the skin. We did try creating slip sensations as well as normal forces, which is shown by these little rotating tactors on the bottom. But we found that there wasn't any difference. Like just providing the normal force is enough, likely because we're just not sensitive enough in the shear direction on the forearm to make the shear information really useful. And that's something we're still exploring, but what we know so far is that it's difficult to provide shear feedback. So all of this prior work brought us to a few challenges. And if we want to have soft wearable skin deformation displays, one is we really need to focus on wearability, comfort, low encumbrance. Joshua also mentioned sound, and these are all issues that we have in our choice of actuators and structural materials. And like Joshua and Irene, I am also like a big fan of pneumatics. I would say worried a couple of years ago that maybe we were backing ourselves into a corner because we weren't sure if we would have a way around building compressors and all of this and noise and such, but I think that we were starting to get there with using pneumatics to enable wearability. I mentioned already reaction forces are a big problem, right? If you want to provide a force on the skin, something else has to be blocking it on the back so that you can provide that necessary force. And as soon as you have this large reaction force or a device that needs to accommodate a large reaction force, then you have increased bulkiness. And so we're trying to figure out how to do that right. And you'll see our solution shortly. And more generally, although I won't talk about this much today, is just larger questions about interaction design. How many degrees of freedom? How do you integrate real and artificial touch? What about multimodal haptic experiences? Joshua mentioned this as well, combining vibration as well as kinesthetic feedback. And this is something that Marcy O'Malley's lab that we've collaborated with them is looking a lot. So I'm going to focus on the first two, which is wearability and reaction forces. And the way that we are doing this now, and we have a paper under review at the moment, is using variable stiffness knitting to be able to seamlessly create hard and soft components in ways where they won't delaminate like they do in typical soft robotic techniques. And there is a huge industry, of course, around knitting. And so we've been learning what they have and how we can exploit that for the purposes of haptics. Some advantages include that there are hundreds of different materials, and we can make them go from very hard to very soft. While it's being knit, it has to be soft due to the knitting process, but you can do heat treatment afterwards with certain materials to make them become very hard after they've been knitted. And especially with modern industrial knitting machines, you can create incredibly complex 2D and 3D shapes. And people do this from things like sweaters to cement scaffolds. And we've been doing this in collaboration with Skylar Tibbitz's group at MIT, in particular with his PhD student Lavender Tesmer and some others, who is just a few examples from their lab just showing the incredible beauty and variability of what they can get out of knitted materials. So let's talk about the device that we made with them and how we integrate pneumatics into it. So I just added this little note on the bottom compared to Irene's pneumatic unit cell, because this is our version of a pneumatic unit cell. The difference is that we are getting the external structure from the knitted fabric rather than the cell. We don't consider that structure that provides the reaction force part of the cell itself. So our cells are very simple. They're just a little pouch made of a 3D printed elastomer, which when you apply air pressure, it balloons out like this. And you can see here just from this figure alone that when you apply the air pressure, it balloons out on both sides. So if you want it to push against the skin and not balloon on the other side, then you need to have some kind of stiff backing. And so the way that we're doing that is with variable stiffness knitting. So on the top here, we have a high stiffness component and on the bottom, low stiffness. So if you put this pneumatic actuator inside, as shown on the left, and then you inflate it with air, it's going to push down on the bottom and you have this rigid backing that prevents it from reducing the force applied to the human by inflating in the other direction. And here's a close-up within our knit structure. On the left, it's uninflated, and on the right, the top part is inflated. And you can't see the back part right now where it's stiff, but you'll see some examples of that in a minute. So how are we getting this variable stiffness from our knit structure? And we do it in two ways. One is through topology variation, and then the other is through material property change. So let's start with the topology variation. So here are three different fabrics. We'll call them A, B, and C. And here's the strain versus force relationships. The idea is that depending on how you knit, like what is the actual topology of the knit, you get different stiffnesses. So you can see significant changes in stiffness just based on how you create the knitting pattern. And rib and jersey, et cetera, are all knitting terms for different patterns. And so even though this topology change gives you quite a bit of difference, it's nothing compared to what happens if you actually vary the materials. And in particular, the way that we did this is we mixed the yarn and its matrix with a thermoplastic fiber, such that after you knit it, we would put it in an oven, and then that thermoplastic fiber would melt and then become very rigid. And so here's three more fabrics, D, E, F, and now you see like orders of magnitude difference in the force strain relationship compared to the more modest changes from the last slide. So here's some examples with, depending on the amount of weight of the thermoplastic fiber versus the regular yarns, how much more stiffness you can get. So overall, if you want to have some topology variation, you can get some variability in stiffness, but if you vary the material, then you get order of magnitude more. And so we can have in a single knit structure sort of 400 times change in stiffness based on the materials and the patterns that we use. I'm just going to say a little bit more about the characterization of those soft pneumatic actuators. I think Irene's pneumatic unit cell has had very similar analysis, so I don't think I'm going to spend much time on it. But the idea is understanding how exactly they deform, being able to characterize, for example, the force, pressure versus displacement properties, and understanding what happens when you have fabric around it or not. I'm going to kind of go through this quickly. And frequency response characterization, jump ahead a little bit more. Let's talk about the sleeve itself now. Once we put these actuators into a sleeve, how do we actually utilize distributed stiffness knitting? So we have flexible hinges between the actuators that help the whole thing be comfortable and wrap to the arm. And so we use a soft fabric for that. We also have a soft fabric areas where we insert hoses for the pneumatic actuation. And you can see we really minimize the hoses in this case, actually, by having just one hose going to each of the different actuators, but there are also ways you can switch between them if you want to have even fewer hoses. We also have other areas where we want it to just be soft due to comfortable fit. And then the place where we really need it to be stiff is on the back side of the actuator, such that the force gets applied to the skin and not ballooning outwards. So briefly, here's the assembly process. We have these flexible pockets where we can put the actuators into it, and then we heat the material to fix the actuators in place and make the backing very stiff. And then because of the soft materials, we have easy access for routing tubes, and then we put those into the device and route them to the pump and controller. This is a kind of a minor thing from a design perspective, but ultimately winds up being very important, which is how does a person actually put this on? And we're looking now at more automated donning and doffing mechanisms. But for this device, what was really important was to have straps that were aligned with each pair of actuators and have them be quite long so that they could fit lots of different arm sizes. So it's pretty easy to put on and can fit a very wide range of people. So I'm going to show this video now, which shows our goal of replicating social touch and focusing on the actuators themselves, which can output 40 newtons each. And then once they're inside the sleeve, here's some examples of the types of patterns that we can create. And then importantly, to Joshua and Irene's point about having a portable pneumatic system, we built on the port flow system from MIT in order to create a wearable device. Still a little bit noisy, but it's actually pretty lightweight. And compared to this entire system, compared to our old system with the voice coil motors, is actually pretty good in terms of its lightweight and compactness. All right, so hopefully that gives you an idea of the function. So our final wearable knit haptic device design is portable, has an untethered pressure source that gets worn somewhere else on the arm. It's a haptic system that it has a suite of different sensations, and overall it's very comfortable and unencumbering. We would like to find ways to make it more breathable. There are definitely a lot of places where the knitted material is quite thick, but we think that that can be improved with optimization in future designs. So it's running a little late for the workshop. I know we took some extra time with the technical difficulties and overall a bit late. So I'm going to kind of blast through this and just hit on a few points, and apologies for skipping some slides. So one point I want to make is that compared to vibration feedback, this type of device is really good for actuator localization. When we have 8 different points of contact, there's really not much point in making them smaller or closer together just because of the limited mechanoreception on the forearm. And so this spacing and this distribution is kind of the best really that we think you can do. So we get fairly good localization of which actuator is being actuated at a particular time. I'm going to skip over some of the social touch materials and just kind of get to the end point, which is that we've done it for the forearm for social touch, but we think there are lots of interesting applications for these types of devices. Teleoperation was mentioned by both of the previous speakers. Guidance and training for sports activities, for someone with a prosthetic limb, how could we provide feedback to other locations of the body where tactile sensing is still complete and intact, and then also navigation. I don't know about you, but my Apple Watch, when it vibrates to give me directions, it is supposed to vibrate differently if it's turn left or turn right. But through a combination of the location on the skin and the fact that I am getting older and my tactile sensing is not as good as that of a very young person, these more deep pressure stimuli, we think may be more effective for a larger swath of the population in terms of giving directional information. So I just want to bring us back to these challenges that we're trying to address through this knit haptics approach. One is to improve wearability. The other is to use distributed stiffness in a really seamless way to provide the necessary reaction forces. And I think this is opening up a bunch of interesting topics that we can study in interaction design. And with that, I want to thank all my students who contributed and our sponsors, and thank you for listening.